everyone. Welcome back to Learning at 11th Hour. Let us continue with the analysis methods. In the previous video, we discussed about how we can apply mesh analysis to an n-mesh network. Today, we are going to be looking at some problems related to mesh analysis, loop current method, and also source transformation. So let us begin with this problem. This problem was asked in the EC paper in GATE 22. So the current I has to be computed for this circuit. So the current I is nothing but the current which is entering the 2 kilo ohm resistor. So now we can apply the loop analysis method. So here let's consider the loop current in this first loop to be I1 and in the second loop to be I2. We can see that these are the only two loops in the circuit. And we can also see that I2 is nothing but the current coming from this current source, which has a current of 1 milliamps coming out from it. So therefore, I2 is nothing but 1 milliamps. Now, in case of the first loop, the current I which we need to compute is nothing but the current I1. So, for the sake of following the steps of mesh analysis, we have considered them to be I1 and I2 so that we can frame the KVL equations for both the loops. So, for loop 1, we can frame the KVL equations by marking the voltage drops. So, in this 2 kilo ohm resistor, which we can see, there are two currents passing into it. One is I1, the other one is I2, both of which are flowing in this downward direction. So that's how the drop would be. And for this 2 kilo ohm resistor, it is going to be from this positive sign to this negative sign. For the 5 volt, it's in this direction. Now let's begin writing the KVL equation at loop 1. So we can see that the direction of the drops that we have assumed is opposing the 5 volts. So we'll say minus 5 plus 2000 I1. Why 2000? Because this is 2 kilo ohms. So I've expanded the kilo as 10 to the power 3 plus, let's look at this 2 kilo ohms. So 2000 into, there are two currents going into it, I1 plus I2. So I1 plus I2. This is equal to 0. Here we know that I1 is I and I2 is going to be 1 milliamp. So we can simplify this equation and write it as 2000 I1 plus 2000 I1 plus 2000 into 10 to the power of minus 3, because I2 is nothing but 10 power of minus 3 amps, is equal to 5. So we can write it as 4000, since I1 is nothing but I, 4000 I is equal to 5 minus, so this 10 power 3 and 10 power minus 3 cancel out, and what remains is just 2, and we can bring it to this side of the equation as minus 2. So therefore, I is nothing but 3 divided by 4 into 10 power 3, which is nothing but 3 by 4 into 10 power minus 3 amps, or 0.75 milliamps. So in this manner, we can compute the current I flowing through this circuit. Let's move on to the next problem. This was a problem that was asked in GATE 2016. And they have actually given us a lot of data over here. We have the voltage source whose value is 25 volts. They have given us the value of voltage drop across this R1 resistor. And they are saying that 14 amps of current is flowing through R2. And they have given us a dependent source over here, which depends on the current I flowing through this circuit coming out from 25 volts. So the problem is that we need to compute the power dissipated by the voltage source. And additionally, I included that we can also compute R1 and R2. So to begin with, we need to know what power really is. So power can be computed by voltage into current. So we know the voltage that comes out from this voltage source, but we do not know the current. If we are able to compute the value of I, we can actually compute the power dissipated by this voltage source. So let us consider the branch current method in order to compute these parameters. So if you look at this particular node, I'll call it as N1. I can actually compute the currents that are entering and leaving this node and form the KCL equation. So at N1, if I apply the KCL, so here we have the current I1 entering N1. So that would be plus I, not I1, that is current I that is entering node N1. And we know that zero point 0.4 I is also entering node N1. So I'll call it as 0.4 I with a plus sign. And we know that 14 amps is coming out of this node. So then we have minus 14. So this is equal to 0. So this is the KCL equation at node N1. Now we can say that 1.4 I is nothing but 14, and therefore I is equal to 14 by 1.4, which is nothing but 10 amps. So we know that the current I is 10 amps. Therefore, the power is going to be 25 into 10 watts, which is 250 watts. So with that, the problem that was asked ends. But we can also go ahead and compute the values of R1 and R2. So in order to do that, let's look at the drop over here. So that says the drop across R1 is 17 volts. Now we can apply Ohm's law. We can say that I into R1 is actually 17 volts. So that means R1 is 17 divided by I ohms, which is nothing but 17 by 10 ohms or 1.7 ohms. We can also compute the value of R2. So in order to do that, we can apply KVL in this particular loop. So here, this is the voltage drop direction marked. So this is already marked. Now because of the current zero point 0.4 I, which is entering and leaving here, the direction of drop because of that dependent current source would be like this. So now we can write the KVL equation for that particular loop as minus 25 plus 17, because they've given us the value of drop itself, plus 14R2 again plus 0.4 into I into R2. So all this put together is 0. We know that the value of I is 10. So zero point 0.4 into 10 is nothing but 4R2. So we can rewrite this equation as 18R2, because 14 plus 4 is 18. 18R2 is equal to 25 minus 17. So we can get R2 as 25 minus 17 is 8 divided by 18 ohms, which is equal to 0.44 ohms. So we can actually obtain the various circuit parameters also, that is R1, R2 values, apart from the value of I and the power dissipated by the voltage source. Moving on to the next problem. So this was a question asked in 2019 in the EE paper of GATE, and we need to compute the value of I flowing through the 20 ohm resistor. So here we can see that all of these voltage sources have a series resistance connected to it. So we can consider that if this is its internal resistance, then we can transform this voltage source into a current source, each of these, keeping in mind the direction of the current. Because for this voltage source, this is positive, this is negative, this is positive, this is negative, this is negative, this is positive, and this is negative, and this is positive. Now, when we transform a voltage source into a current source, we need to ensure that the arrow of the current source is pointing towards the positive of the voltage source. So, let me transform this first voltage source into a current source. So in order to do that, we know that V is equal to IR. So we know voltage is 200 and we know that the resistance is 50. So that will give us nothing but 4 amps. So what we get here is we get a 4 amps current source, the arrow being in that direction, This is a 4 amps current source with a 50 ohms in parallel with it. Similarly, we can transform the second one, the 160 volts voltage source, into a current source. So we'll get 160 divided by 40, which is again 4 amps. So another 4 amps current source with a 40 ohms in parallel with it. Next, we can convert the 100 volt voltage source into a current source. So what we get is 100 divided by 25, which is again 4 amps. And this time the direction should be pointing towards the positive of the voltage source. So it is going to be pointing downwards like this. So that would be 4 amps with the 25 ohms in parallel with it. And lastly, we can actually convert this 80 volts as 80 divided by 20, again 4 amps. And this time also, the direction of the current should be pointing towards the positive of the voltage source, and therefore it is going to be downward. So this is also 4 amps with 20 ohms in parallel with it. So we are now going to put all of these current sources in parallel with each other. It is possible because the magnitude of current from all of these current sources is the same. So we have first one, the 4 amps with 50 ohms in parallel with it, followed by 4 amps with the 40 ohms in parallel with it, followed by the 4 amps pointing downwards, and 20 ohms in parallel with it, followed by another 4 amps pointing downwards with the, so this is 20 ohms, this is 25, and this is 40 ohms in parallel with it. Lastly, we have to connect the resistor under consideration, which is the last 20 ohm resistor through which we need to compute the current I. In order to make it look a little simpler, let's put all the current sources together. So this is the first 4 amps, this is the second 4 amps, this one pointing downwards is the third one, and this is the fourth 4 amps. Now connected with this would be the resistor, I'll call it as R, where R is going to be nothing but 1 by 50 plus 1 by 40 plus 1 by 25 plus 1 by 20, the whole inverse, because they are all parallel to each other. And this is going to be in parallel with the 20 ohm resistor in concern, through which we need to compute I. So now if you look at this particular node, what are the currents that are entering and leaving? So there are two 4 amps that are entering and two 4 amps that are leaving. Therefore, effectively, the current that is coming out of this node is going to be equal to 0. So therefore, the value of I in this problem is 0 amps. So I hope the solution to these problems was clear to you. The intuition as to how to approach a particular problem and what method to implement in order to arrive at the solution with no error and quickly, well, that will come with sheer practice. So just keep practicing, come across different problems from the books that have been mentioned in the description of my first video. Uh, Please do drop in your comments if you have any queries. Thanks for watching.